The wormhole myth and the real question. If you think wormholes are just cosmic shortcuts, this series is going to ruin that, in a good way. Here's the shortcut myth. A wormhole is a tunnel you can fly through to pop out somewhere else, fast. In reality, wormholes are real solutions in Einstein's equations. But a solution on paper is not the same thing as a usable tunnel in nature. So, the real question isn't, do wormholes exist? It's what would it take for a wormhole to be physically real, stable, and traversable. And here's why this gets serious. The math that creates wormholes also shows up in black holes. And black holes force one of the deepest puzzles in physics. What happens to information? In this series, we're going to separate three things: what the equations allow, what physics seems to forbid, and what's still genuinely open. We'll start with what Einstein-Rosen Bridges actually are and why they pinch off. Then we'll talk about what traversable would require. And then we'll follow the thread into the black hole information paradox, because that's where wormholes stop being sci-fi and start being a real problem. By the end, you'll be able to hear a wormhole claim and instantly ask the right questions. What energy conditions does it violate? What's the time scale? What's the trade-off? If you love mind-bending science without the hype, subscribe to sciByte Insights. Complex science, simple explanations, every day. So, what do we actually mean when we say wormhole? Here are definitions you can trust, so we stop arguing about different things. Wormhole is one of those words that got stretched by sci-fi, headlines, and even physicists using shorthand. So before we talk about what's possible, we need to lock down the vocabulary. An Einstein-Rosen bridge is a specific thing. It's a geometric connection that shows up in the maximally extended black hole solution. It looks like a bridge on a space-time diagram, but it's not a tunnel you can ride through. A traversable wormhole is the stronger claim, a throat that stays open long enough for matter or signals to pass through, without hitting a singularity or being crushed by a horizon. Traversable isn't a vibe. It means at least three things. 1. The throat doesn't pinch off before you cross. 2. Tidal forces don't shred you. 3. The trip doesn't require infinite acceleration or impossible timing. An bridge fails the first requirement almost immediately. In the classic picture, it pinches off so fast that nothing can get from one side to the other. Historically, people used wormhole as a convenient label for space-time connection, even when the connection wasn't usable. That's where the confusion starts. The same word gets used for both a diagram feature and a physical tunnel. So here's the rule for this series. If it's an bridge, we'll call it an bridge. If it's traversable, we'll say traversable wormhole, and we'll ask what keeps it open. And if someone just says wormhole, we'll demand which one they mean. Einstein-Rosen Bridges, 1935. This is the original wormhole idea, before sci-fi got involved. This is pure geometry. Not a spaceship tunnel, not a portal, just what Einstein's equations allow you to draw on paper. In 1935, Einstein and Rosen noticed something strange in the math of a black hole. It looks like space-time can be extended, so you get two outside regions connected by a bridge. An Einstein-Rosen bridge is a connection between two exterior regions in an idealized black hole spacetime. It's a feature of the maximally extended solution, basically, the full mathematical continuation. The easiest way to picture it is two universes or two far-apart regions, each with their own outside. And at one instant in time, there's a narrow throat connecting them. But here's the catch. That throat is not a stable structure you can hold open. In the classic bridge, the geometry evolves, so the throat pinches off. So why does it get called a wormhole? Because on a diagram, it looks like a shortcut. But looking like a shortcut is not the same as being a traversable path. When you hear maximally extended, think, we're not stopping the math at the first coordinate breakdown. We're extending the solution to include every region the equations describe. So, bridges prove something important, but limited. General relativity contains spacetimes with bridge-like connections. They do not, by themselves, give you a usable tunnel for matter or messages. Why bridges aren't traversable in standard general relativity? This is the pinch-off. The bridge exists, but not as a route you can take. Remember our definition. Traversable means a signal or a person can go from one side to the other. So the question is simple. In the original bridge geometry, can anything actually cross? In standard GR, the answer is no. The bridge is not a stable tunnel. It closes too fast. Here's the key intuition. The throat shows up on a snapshot of spacetime, one slice of time. But when you look at the full movie, that throat is already collapsing. Think of it like a doorway that exists only at the exact instant you take a photo. By the time you try to walk through, the door is gone. And this isn't a go faster problem. Even light can't make it through in the classic bridge. The geometry doesn't give you a path that stays open long enough. From the outside, you see a black hole horizon. From the inside, the spacetime funnels you toward a singularity. The bridge doesn't connect two safe outsides you can travel between. It connects regions in a way that's non-crossable. So, if someone says wormholes are real, therefore shortcuts are real, this is the correction. bridges are real in the math, but standard GR does not give you a usable shortcut. Which immediately raises the next question. If the bridge pinches off in standard GR, what would you have to add to keep a throat open? Traversable wormholes, Morris Thorne. What would it actually take to keep a throat open? Up to now, we've been talking about bridges, real geometry in GR, but not crossable. Morris and Thorne asked a different question. If you wanted a wormhole you could actually travel through, what conditions would the spacetime need? A traversable wormhole is a spacetime with two mouths and a throat that stays open long enough for signals or matter to pass through safely. First requirement: the throat can't pinch off before you cross. So the geometry has to be supported, held open against its natural tendency to collapse. Second, the tidal forces have to be small enough that you don't get ripped apart. That means the curvature near the throat can't be too extreme, at least not on human scales. Third, you can't have an event horizon sitting in the way. If there's a horizon, you can fall in, but you can't send a message back out. Traversable means two-way communication is possible. Fourth, it has to be usable in practice. Crossing shouldn't require infinite acceleration, perfect timing, or a trip that takes longer than going the long way around. And here's the famous catch. In standard classical physics, the kind of matter we know doesn't naturally provide the stress energy you need to hold a throat open. In the simplest models, you need something that behaves like negative energy density in the right place. Negative energy doesn't mean anti-gravity magic. It means, compared to ordinary matter, the energy and pressure pattern has to push spacetime the opposite way, so the throat doesn't collapse. Quantum physics can produce negative energy in small, constrained ways. The hard part is scale and stability. Can you get enough of it in the right shape for long enough without breaking everything else? So yes, you can write down traversable wormhole geometries, but the requirements are not a footnote, they're the whole story. Allowed by equations is not the same as achievable in nature. Why black holes are where this gets serious? Because horizons turn cool geometry into a physics problem. Up to now, wormholes might feel like a math curiosity. Black holes are where the stakes jump, because black holes come with horizons. An event horizon isn't a solid surface. It's a boundary in space-time. Cross it, and according to classical GR, you can't send a signal back out. And that one-way rule is basically causality in action. It decides which events can influence which other events. Now connect the dots. Einstein-Rosen bridges show up when you extend the math of a black hole. So wormhole-like structure isn't something we bolt on, it's baked into the geometry of horizons. Here's the test that keeps showing up in this whole story. If I fall toward a black hole, what information about me can the outside universe still access? Classically, black holes look like ultimate erasers. Stuff falls in, the horizon hides it, and the interior ends at a singularity. If that's the full story, information seems to disappear from the outside world forever. But quantum physics is built on a different rule. The evolution of a closed system is reversible in principle. So information is destroyed isn't just sad, it's a fundamental clash. And that's why wormholes keep coming back. Not because we want sci-fi travel, but because bridges and horizons are the same mathematical neighborhood where the information problem lives. So, next we need the twist that turns this into a real paradox. Hawking radiation. Black holes aren't perfectly black. Hawking radiation. The fact that forces the paradox. Classically, black holes only swallow. Hawking's result says, black holes also emit. Hawking radiation is a very faint thermal glow that comes from a black hole, because quantum fields don't stay quiet near a horizon. This is not a beam shooting out from inside the hole. It's a quantum effect tied to the horizon itself and to what different observers call vacuum. One common intuition is quantum fluctuations create pairs near the horizon. One partner falls in, the other escapes. That picture isn't the full math, but it's a useful mental model for the punchline. The punchline is real. The escaping radiation carries energy away, so the black hole loses mass. Given enough time, it can evaporate. Here's the problem. The radiation is thermal. It looks almost featureless, like it doesn't remember what fell in. So now combine two statements. 1, the horizon hides what falls in. 2, the black hole radiates away and can disappear. If the radiation doesn't carry the information out, where did the information go? General Relativity says, once you cross the horizon, the outside can't get signals from you. Quantum theory says, in standard formulations, information isn't supposed to just vanish. Those two ideas collide right here. Think of it like a ledger. Stuff falls in, the outside loses access. Radiation comes out, the black hole shrinks. When the hole is gone, the ledger still has to balance. The information paradox, explained like a ledger, what has to balance. When physicists say information, they don't mean secret messages. They mean the full physical description of a system, everything you'd need in principle to predict what it can do next. Here's a simple example. If you burn a book, the words look destroyed. But in physics, the smoke, heat, and ash still carry the microscopic details, scrambled, but not gone. In standard quantum theory, the evolution of an isolated system is reversible in principle. So if you had perfect access to every microscopic detail, you could run the story backward. Now, drop something complicated into a black hole, say that book. From the outside, all you can track is a few bulk properties: mass, spin, and charge. All the fine detail seems to vanish behind the horizon. Then, Hawking radiation comes out, and it looks thermal, like heat, random, featureless, not carrying a readable fingerprint of what fell in. Here's the ledger. On the inside, a detailed quantum state, lots of information. On the outside, radiation that looks like a bland thermal state. If the black hole fully evaporates, the in and out have to match in a deep way, not just in energy, but in information. So, the paradox is this. If the radiation is truly thermal and uncorrelated with what fell in, then the final state looks more random than the initial state. That would mean information was destroyed. And this isn't a taste issue. If information can be destroyed, then quantum theory as we use it stops being predictably reversible. It changes what cause and effect even means at the most fundamental level. So, what would a resolution look like? It's not, we found the information somewhere. A real resolution needs a consistent story where, 1. The outside radiation ends up carrying the information, maybe in subtle correlations, or 2. The black hole doesn't fully evaporate, leaving a remnant that stores it, or 3. Our assumptions about horizons, locality, or quantum theory have to change. And whatever the answer is, it has to respect the hard constraints: energy conservation, causality, and the fact that distant observers can't just reach behind the horizon whenever they want. Approach number 1. Information is lost. The original answer, and why it detonated physics. Before the modern solutions, there was a blunt historical position. Maybe black holes really do destroy information, not as a meme, as a real claim about how nature works. Because in the classical picture, it's hard to see any other outcome. Matter falls in, the horizon blocks communication, and the interior ends at a singularity. From the outside, the detailed story seems permanently inaccessible. Then, Hawking radiation adds the twist. The black hole can shrink and disappear. So now it's not just hidden behind a horizon. It's gone from the universe we can describe. So, the historical claim is, a pure, detailed quantum state can evolve into a mixed, thermal-looking state. In plain English, the universe can forget. And at first, that didn't sound crazy to everyone, because we already deal with information loss in everyday physics, like mixing cream into coffee. The difference is that everyday loss is about practical ignorance, not fundamental erasure. If black holes destroy information fundamentally, you don't just solve a paradox, you rewrite quantum theory. You'd need new rules for how probabilities evolve and how the universe stays consistent. And it wouldn't stay contained inside black holes. If information can be destroyed in one place, it threatens predictability everywhere, because quantum systems can be entangled across huge distances. There's also a bookkeeping worry. Changing the rules of quantum evolution can create side effects, like violations of conservation laws or weird non-local behavior, unless the new theory is extremely carefully built. So, over time, the pressure built in the other direction. Maybe the radiation isn't truly featureless. Maybe the information is still there, encoded in subtle correlations we weren't seeing in the early story. Even if you don't like information is lost, it did something important. It forced physicists to say exactly what must be preserved and what assumptions we're willing to sacrifice. Approach number 2. Black hole complementarity. How you save information without letting anyone verify a contradiction. We've got a tension. From far away, Hawking radiation looks thermal, like it can't carry the details out. But quantum theory expects the ledger to balance. Complementarity is an attempt to keep both, by changing what counts as a single global story. Black hole complementarity says, different observers can have different, consistent descriptions of what happens, and no observer can compare notes in a way that reveals a contradiction. Picture two observers. Observer A stays far away with a telescope. Observer B falls in. They're both describing the same black hole, but they don't agree on what's really happening at the horizon. In the outside description, the horizon acts like a hot quantum membrane. Stuff falls toward it, gets scrambled, and the information is re-emitted, extremely mixed up in the outgoing radiation. So from the outside, no fundamental information loss. But for the infalling observer, the horizon doesn't feel like a wall. In classical GR, you cross it without noticing anything dramatic, at least for a large black hole. So from the inside, you just fall through. And here's the trick. If observer B crosses the horizon, they can't send a message back out to compare notes. If observer A waits outside collecting radiation, they can't then jump in and verify the same information is also inside. Not in any operational way. So the theory says you never get a single experiment that forces both stories to be true at once. Think of it like two maps of the same city. One map is perfect for driving. Another is perfect for the subway. They don't match street by street, but each is consistent in the situations where you can actually use it. Complementarity is saying physics might work like that near horizons. What is complementarity trying to preserve? 1. The outside world gets a unitary, information-preserving evolution. 2. The infalling observer doesn't hit a literal brick wall at the horizon. 3. Causality stays intact. No messages from inside to outside. The obvious criticism is, wait, are you saying the information is both reflected and also passes through? That sounds like cloning, the same quantum information existing in two places. Complementarity's answer is, you can't operationally access both copies, so the contradiction never becomes physical. And that's why complementarity became a battleground. It's not just a technical fix, it's a philosophical shift. It treats what happened as observer-dependent in a very specific, constrained way. The question is whether that's a deep truth or a patch that breaks when you push it hard enough. Approach number 3. Firewalls. The argument that a smooth horizon might be impossible. Complementarity tried to keep two things true at once. From far away, information escapes in the radiation. For the infalling observer, the horizon is smooth. Firewalls is the claim that you can't keep both. Here's the problem Firewalls targets. If black holes evaporate and information is preserved, then late-time Hawking radiation can't be completely random. It has to be correlated with earlier radiation. And in quantum physics, correlations aren't just similarity, they can be entanglement, a shared quantum link where two pieces behave like parts of one bigger state. Now comes the pressure point. A single quantum system can't be maximally entangled with two different independent systems at the same time. If you try to force it, the math says something has to break. In the usual smooth horizon picture, a Hawking particle outside is strongly entangled with a partner mode just inside the horizon. That's what makes the horizon look like empty space to someone falling in. But if the black hole is old and information is coming out, that same outside particle also needs strong correlations with the earlier radiation already far away. So, AMP said, pick your sacrifice. Either 1. Information doesn't come out, Unitary fails. 2. Effective physics outside the horizon breaks down in a dramatic way. Or 3. The horizon is not smooth. Their conclusion was the third option, a firewall, high-energy drama at the horizon. Important: firewall isn't a literal wall of flames. It's a name for a breakdown of the usual nothing special at the horizon idea. Instead of crossing smoothly, the infalling observer hits violent quantum effects right at the horizon. And that's why it hit like a bomb. General Relativity's big promise is, for a large black hole, the horizon is locally boring. Firewalls says, no, the horizon could be a physical, destructive boundary. If Firewalls is right, then the black hole acts less like a quiet region of spacetime and more like an information processing surface with real, energetic consequences. It would mean the smoothness of spacetime is not guaranteed when quantum information is on the line. Of course, physicists immediately looked for escape routes. Can the correlations be more subtle than we assumed? Can spacetime itself reorganize the bookkeeping? Or is the inside description not independent in the way the argument assumes? Those questions lead directly into the next approaches. Approach number 4, ER equals EPR, the wild idea that entanglement might literally be geometry. Firewalls was a pressure test. If information comes out, late radiation must be correlated with early radiation, and that seems to break the smooth horizon. ER equals EPR is one of the most famous attempts to dodge that conclusion by changing what inside even means. ER equals EPR proposes a link between two things that used to feel unrelated. ER, Einstein-Rosen Bridges, basically wormhole-like connections in spacetime, and EPR, quantum entanglement. In slogan form, entanglement and wormholes might be two descriptions of the same underlying connection. Important: this is not saying you can use entanglement to build a Star Trek shortcut. These wormholes are typically non-traversable. They don't let you send signals faster than light. The claim is about bookkeeping, what counts as connected in the deep structure of physics. Here's the intuition. Take two quantum systems that are maximally entangled. Even if they're far apart, their states aren't independent. They behave like two ends of one shared object. ER equals EPR says, maybe spacetime connectivity works the same way. Now apply that to black holes. If an old black hole is entangled with its Hawking radiation, then the black hole plus radiation might not be two separate things. The inside description could be stitched together with the radiation through an ER-like connection, a geometric way to represent the entanglement. And this is the key. Firewalls treat the inside partner mode and the early radiation as independent systems competing for entanglement with the late particle. ER equals EPR suggests they might not be independent in the first place. If the interior is encoded in or connected to the radiation via this ER-like structure, the triangle changes shape. So what is ER equals EPR trying to preserve? 1. Unitarity. Information isn't destroyed. 2. No faster-than-light signaling. 3. A smooth horizon for the infalling observer, without pretending the radiation is featureless. It's a proposal that the inside is not a separate place with separate degrees of freedom. Does ER equals EPR make a simple, direct prediction you can test tomorrow? Not really. It's more like a consistency map. It tells you what a successful quantum gravity theory might have to look like. It pushes you toward the idea that spacetime geometry can emerge from entanglement patterns. And it has real open problems. How exactly does a smooth interior emerge from messy radiation? What does the wormhole mean in a precise, calculable model? And how do you avoid sneaking in contradictions under a new name? ER equals EPR is a direction, not a finished machine. But ER equals EPR changed the conversation. It made geometry from information feel less like poetry and more like a working research program. Instead of asking, where did the information go, you start asking, what is space-time made of if entanglement can act like glue? Approach number 5, islands and the page curve. The moment the math starts giving information back. Firewalls said the bookkeeping doesn't add up. Late radiation can't be linked to both the interior and the early radiation. Islands is the approach that answers with something bold. Maybe we were counting the inside wrong in the first place. The goal is simple to say. If information is preserved, then the radiation shouldn't stay thermal forever. At some point, the radiation should start looking more and more like a complete record of what fell in. That expected rise and fall pattern is called the page curve. Imagine tracking one number. How much hidden information is still trapped in the black hole? Early on, the radiation looks random, so that hidden information grows. But after a turning point, the page time, it should reverse. Late radiation should carry out the details, and the hidden information should drop back down. But Hawking's original calculation gives the wrong shape. It says the radiation stays thermal the whole time, so the hidden information just keeps climbing, even as the black hole disappears. That's the paradox in draft form. Islands says, when you compute the entropy of the radiation, you're not always allowed to treat the black hole interior as completely separate. In certain regimes, the best calculation includes an island, a region that looks like it's inside the black hole, as part of the radiation's entanglement bookkeeping. It's like the accounting ledger suddenly says, this chunk belongs on the radiation side of the books. So, what's an island? It's not a physical landmass. It's a region of spacetime that gets included when you ask, what information is actually encoded in the radiation? The shocking claim is, the radiation's description can effectively own part of what we used to call the interior. And when you include islands, the curve changes. Early on, you get Hawking's thermal behavior. But after the page time, the calculation flips to a different dominant contribution, and the result is the page curve. The entropy turns around and information comes back out. Not as a philosophical slogan, as a concrete result of the math. So, what does this approach preserve? 1. Unitarity, no fundamental information loss. 2. Semi-classical gravity still works surprisingly far. 3. No need for a permanent firewall everywhere. The cost is conceptual. The boundary between inside and outside is not as absolute as we thought. Islands doesn't give you a lab experiment tomorrow, but it does give you a target. Any correct theory should reproduce the page curve, and it implies something deep. The black hole interior may be encoded in the radiation, in a very literal information-theoretic sense. And there are open questions. What exactly is the microscopic mechanism for that encoding? How does the interior reconstruct from the radiation without paradoxes? And how general is this result beyond the models where we can calculate cleanly? Islands is powerful, but it's not the final word. Approach number 6, Fuzzballs. The idea that the interior might not exist at all. Firewalls says, if information comes out, the horizon can't stay perfectly smooth. Island says, the bookkeeping changes, and the page curve comes back. Fuzzballs is a different kind of answer. Maybe we should stop imagining a black hole as empty space inside a smooth horizon. Fuzzballs proposes that what we call a black hole is actually a quantum object made of microstructure, a huge number of possible microstates. From far away, it can look like an ordinary black hole, but up close, there may be no featureless horizon and no classical interior. Here's the intuition. In the classical picture, the horizon is like a clean boundary. Outside is normal space, inside is a hidden region. Fuzzballs says, instead of a clean boundary, the whole object is more like a tangled ball of threads, structure all the way down. There isn't a single empty inside to fall into. And that matters, because information can't escape from nothing. If the black hole is actually microstructure, then radiation can, in principle, carry information the way heat from a hot object carries details about what it's made of. Not by magic, by ordinary quantum evolution of a complicated system. So, what does Fuzzballs try to keep true? 1. Unitarity. Information isn't destroyed. 2. The outside, far from the whole, still looks like general relativity, but it sacrifices a comforting idea that there's a smooth horizon with empty space just inside. Now, does this mean you hit a literal wall? Not necessarily in a simple cartoon way. Different microstates can look different up close. The claim is the classical no-drama horizon may be an approximation, and the exact quantum description has structure where GR says there's nothing special. Fuzzballs isn't a single finished model you can point to and say, that's the one. It's a program. Build explicit microstates and show they reproduce black hole properties. If it's right, it implies the interior is emergent, a coarse-grained story, not a fundamental place. And there are real open problems. Can fuzzball microstates be constructed for realistic astrophysical black holes, not just idealized cases? How does an effective interior emerge for an infalling observer, if it emerges at all? And how do you connect this picture cleanly to the page curve and the island results? But Fuzzballs is important because it flips the default assumption. Instead of asking, how does information leak out of a smooth horizon? It asks, what if the horizon was never empty in the first place? That's a radical move, and it's one of the clearest ways to avoid the paradox. Approach number 7. Remnants and baby universes. The idea that the information survives because the black hole never truly ends. Firewalls says the smooth horizon story may break. Island says the math can return the page curve. Fuzzballs says the interior might be replaced by microstructure. Remnants and baby universes are a different kind of escape hatch. Maybe the information doesn't come out in the radiation at all, at least not in any simple way. Remnants is the claim that evaporation stops at the end. Instead of disappearing completely, the black hole leaves behind a tiny leftover object, a remnant that still contains the information. Intuitively, it's appealing. If the information can't get out fast enough, just keep it stored. Like a hard drive you can't read from far away, but it still exists. But here's the problem. A big black hole could have swallowed an enormous amount of information. If the final remnant is tiny, maybe near the Planck scale, then it would need an absurd number of internal states to store all that information. That's not impossible in principle, but it creates serious consistency headaches. If there are infinitely many possible remnant states, physics starts to look unstable. You'd expect remnants to be produced too easily, because there are so many ways to make them. It's like having a lottery with infinite winning tickets. Probabilities stop behaving normally. Baby universes is the cousin idea. Instead of the information staying in our universe, it escapes into a new region of space-time, a baby universe that branches off behind the horizon. From our point of view, the black hole evaporates, but the information isn't destroyed. It's just gone somewhere we can't access. And that's why it's controversial. If the information leaves our universe, then for us, it still looks like information loss. You can say unitarity is saved globally, across a bigger multiverse bookkeeping. But locally, in our observable world, predictability may still fail. So what does this approach preserve? It preserves the idea that nothing truly gets destroyed, but it sacrifices something else, that the information is recoverable from the Hawking radiation in our universe. In a sense, it trades information loss for information inaccessibility. Does it give a clean, testable signature? Usually not. Remnants would be tiny and hard to detect. Baby universes would be, by definition, causally disconnected. So this approach is mostly judged by theoretical consistency. Does it avoid paradoxes without breaking the rest of physics? And that's why many physicists are skeptical. Remnants risk runaway production and infinite state counting problems. Baby universes risk making our universe fundamentally non-unitary in practice. These ideas might be possible, but they come with heavy costs. Still, remnants and baby universes matter because they show the menu of options. If you refuse to change the horizon story, and you refuse to encode the interior in the radiation, then the only place left for the information is somewhere else. Approach number 8. A new bridge reinterpretation. A way to make the paradox dissolve by changing what the bridge means. By now, you've seen the menu of answers. Firewalls change the horizon. Islands change the bookkeeping. Fuzzballs change the interior. Remnants and baby universes change where the information goes. This 2026 proposal tries something different. It revisits the Einstein-Rosen Bridge itself and asks whether we've been interpreting that geometry too literally. The problem is still the same. Hawking radiation looks thermal, but quantum mechanics says information shouldn't be destroyed. So the question is, what's the correct story that keeps gravity and quantum rules consistent? Here's the core move, stated carefully. The proposal suggests that an bridge shouldn't be treated as a normal inside tunnel you could assign information to in the usual way. Instead, the bridge is reinterpreted as a kind of bookkeeping structure, a geometric way of representing correlations, where what counts as interior information depends on how you define the quantum state across the horizon. In other words, the bridge is real in the math, but its meaning is more subtle than a place you could store secrets. Think of it like this. Sometimes a picture isn't a photograph, it's a diagram. This approach treats the bridge less like a literal tunnel and more like a diagram that tracks which degrees of freedom are linked to which. So when the entanglement pattern changes during evaporation, the bridge interpretation changes too. And that's what it's trying to solve. 1. Keep unitarity, no fundamental information loss. 2. Avoid adding new violent physics at the horizon. 3. Keep the semi-classical picture useful, but admit that the naive inside-outside split can mislead you. The pitch is, the paradox partly comes from treating the bridge as a classical object with a classical interior. If this reinterpretation is right, it implies something pretty striking. The interior isn't a fixed container you can talk about independently. It's a description that depends on the quantum correlations you're using, and those correlations can be encoded in the radiation. So instead of asking, how does information escape the tunnel, you ask, why did we think the tunnel was the storage unit in the first place? Now, this doesn't automatically replace islands or equals EPR or complementarity. It's closer in spirit to the idea that geometry and entanglement are two languages for the same underlying thing. But the emphasis here is different. It's specifically about rereading the bridge so the usual paradox bookkeeping doesn't even start. And the big open issues are exactly what you'd expect. What is the precise microscopic mechanism that makes this reinterpretation more than a relabeling? How do you compute the page curve in realistic settings using this picture? How do you define what an infalling observer experiences without sneaking in a firewall through the back door? And most importantly, what unique, checkable consequences does this proposal have that distinguish it from other stories? Even if it turns out incomplete, it's interesting for a simple reason. It attacks the paradox at the level of interpretation, the meaning of the geometry, not just the equations. It's a reminder that in quantum gravity, where the information is might be the wrong question. The right question might be, what are we allowed to call an interior, and when? What this all means, and doesn't mean. The clean myth bust, the real lesson, and the right questions. Quick recap of what we did. We started with the wormhole myth. Then we separated bridges from traversable wormholes. Then we hit the real problem. Hawking radiation forces a clash between gravity and quantum rules. Everything after that was different ways physicists try to make the story consistent. First myth. Wormholes are shortcuts we can use. In standard general relativity, the Einstein-Rosen Bridge is not a traversable tunnel. It pinches off too fast. So if you're imagining a spaceship route, that's not what the math gives you. Second myth. The paradox means physics is broken. No. It means two extremely successful frameworks are being pushed into a regime where our usual assumptions collide. That's not a failure. That's how progress happens. The paradox is a stress test. Third myth. Hawking proved information is destroyed. Hawking's calculations showed the radiation looks thermal in a semi-classical approximation. The debate is what the full quantum gravity story is. So the honest takeaway is, the calculation is real. The interpretation is still being refined. Fourth myth. We solved it. Different approaches fix different parts of the story, and they come with different costs. Some change the horizon. Some change what you count as inside. Some replace the interior with microstructure. Some move the information somewhere else. And some, like the newer reinterpretations, try to dissolve the paradox by rethinking what the geometry is actually telling you. None of that is the same as a confirmed final theory. Here's the clean, unifying picture. The paradox is basically one question. Can the outside world, using only the radiation, tell a unitary story about what fell in? Every approach answers by changing one of these assumptions. 1. What the interior even means. 2. Whether the horizon is smooth. 3. Whether semi-classical gravity is valid all the way through evaporation. 4. Whether information is recoverable in our universe at all. And that's the real lesson. In quantum gravity, geometry may not be a fixed stage. It may be an emergent description of quantum information, correlations, entanglement, and coarse graining. So a lot of the confusion comes from asking classical questions. Where is the information located? In a regime where location itself may be the wrong primitive. Rapid-fire bad takes to delete from your brain. 1. Black holes are portals. 2. Wormholes let you time travel by default. 3. Hawking radiation is just heat, so it can't carry information. 4. If information comes out, you must hit a firewall. Reality is more subtle. The radiation can be thermal-looking early and still be part of the unitary process, and the interior horizon story might be state-dependent or emergent. So what are the right questions? 1. What does it mean for an interior to be well-defined in a quantum theory? 2. What is the microscopic mechanism that makes the page curve come out right? 3. What does an infalling observer actually experience, and can that be defined consistently? 4. What predictions would let us distinguish these stories, even indirectly? If you can track those questions, you're thinking like a physicist, not a sci-fi writer. And that's the whole story. Wormholes aren't the shortcut. The paradox isn't a gimmick. It's a clue about how space-time and information fit together. Subscribe to sciByte Insights. Complex science, simple explanations, every day.